A clock ticks slower near a cosmic giant than it does on Earth. This is the proven reality of time dilation, a fundamental feature of our universe where gravity warps the very fabric of space-time. By the end of this journey, you will understand how these celestial giants are rewriting the rules of time and space. We will uncover how a black hole can stretch a single second into an eternity and explore what this teaches us about the true nature of existence. What does it mean for our reality if time itself is not a constant river, but a fluid, changing dimension? This cosmic canvas, this fabric of space-time, is not a passive stage. It is a dynamic participant in the drama of the universe. Think of it as an immense, invisible trampoline, perfectly still until you place a heavy bowling ball in its center. The ball sinks, creating a deep well. Now roll a marble across the stretched surface. Instead of traveling in a straight line, the marble curves, spiraling inward along the contours of the depression. This simple analogy reveals a profound truth. The planets in our solar system are not being pulled by some mysterious, invisible force from the sun. They are simply following the natural curves, the grooves etched into space-time by the sun's immense mass. Even light, which has no mass, must follow these curves. A beam of starlight passing near the sun will bend ever so slightly, its path altered by the star's gravitational dent. This bending is not magic, it is geometry. The presence of mass and energy tells space-time how to curve, and the curvature of space-time tells everything within it how to move. But what happens when this curvature becomes extreme? When the fabric is not just dented, but stretched and twisted to its very limits? This is where the true mystery of time begins to unravel. This geometric view of the cosmos was a radical departure from everything that came before. For centuries, we understood gravity through the work of Isaac Newton, who described it as a mysterious, invisible force that reached out across empty space to pull objects together. But Albert Einstein saw something else entirely. In 1915, he presented his theory of general relativity, which fundamentally rewrote the script. Einstein proposed that gravity is not a force at all. Instead, it is a consequence of the shape of the universe itself. Mass and energy, like that of a star or a planet, actually warp the fabric of space-time around them. Think of a soft mattress. A bowling ball creates a deep indentation, and a nearby marble will naturally roll toward it. The marble is not being pulled by a force, it is simply following the curve of the mattress. This is the essence of Einstein's revelation. His field equations provided the mathematical language for this cosmic dance, stating that matter tells spacetime how to curve, and that curved spacetime, in turn, tells matter how to move. This single idea predicted incredible things, such as the bending of starlight around the sun, which was later confirmed during a solar eclipse. It also directly predicted the slowing of time in stronger gravitational fields. By reframing gravity as geometry, Einstein gave us the key to understanding the most extreme environments in the universe, places where the fabric of reality is not just warped but torn. This slowing of time, known as time dilation, is not a flaw in the clocks. It is a fundamental feature of reality. Think of two perfectly identical clocks. One sits on your desk, and the other is placed closer to a massive object, like a dense planet. The clock near the planet will begin to fall behind, ticking fewer times than the one on your desk over the same period. This difference is the result of gravitational potential, a measure of the intensity of the gravity field. The stronger the gravity, the deeper the well in space-time, and the more time itself is stretched and slowed. We have confirmed this with astonishing precision. Atomic clocks, the most accurate timekeeping devices ever built, show a measurable difference between one placed on the ground and another flown on a high-altitude airplane. The higher clock, experiencing slightly less of Earth's gravity, runs just a tiny bit faster. This proves that the effect is real, not theoretical. The flow of time is not universal. It is a local phenomenon dictated by the shape of the space you occupy, and this concept, so subtle on our planet, becomes the dominant rule near the universe's most powerful objects. These cosmic giants are the true masters of gravity, where the subtle slowing of time becomes an overwhelming force. A black hole represents the most extreme case, a region of space where gravity has become so intense that the fabric of spacetime is twisted into a one-way street. At its boundary, the event horizon, the gravitational pull is so powerful that the velocity required to escape exceeds the speed of light itself. Since nothing can travel faster than light, nothing, not even a single photon, can ever return. It is a point of no return where the warping of time becomes absolute. Just outside this boundary, time slows to a crawl relative to the outside universe. A single second for an object hovering there could stretch into years, decades, or even millennia for a distant observer. But black holes are not alone in their ability to warp time. Neutron stars are their incredibly dense cousins. These are the collapsed cores of massive stars that exploded in supernova. A typical neutron star packs more mass than our entire sun into an object no wider than a city. The gravity on its surface is so ferocious that it crushes atoms into a sea of subatomic particles. Time on the surface of a neutron star passes significantly slower than time in the emptiness of interstellar space. Even within our own solar system, the gas giant Jupiter, with its immense bulk, creates a measurable gravitational time warp. A clock on Jupiter would tick slower than a clock on Earth, though the difference is incredibly small. These celestial bodies, from the planet to the stellar corpse to the ultimate cosmic vacuum, are natural laboratories. They allow us to observe the predictions of general relativity pushed to their very limits, showing us a universe where time is not a constant backdrop, but a dynamic, malleable dimension shaped by the presence of mass and energy. While Einstein's equations painted a grand theoretical picture, it took a brilliant mind to find a precise map for this new reality. Karl Schwarzschild, a German physicist, accomplished this feat while serving on the front lines during the First World War. Amidst the conflict, he studied Einstein's papers and discovered the first exact solution to the field equations. His work described the gravitational field surrounding a perfectly spherical, non-rotating object. This mathematical description, now known as the Schwarzschild metric, became the key to unlocking the secrets of black holes. It introduced a critical concept, the Schwarzschild radius. This is the specific distance from the center of a mass where the escape velocity equals the speed of light. It defines the event horizon, the point of no return. The mathematics reveals a staggering consequence. As an object falls toward this boundary, an outside observer would witness something profoundly strange. The object would appear to slow down, its light reddening and dimming as time for the object stretches relative to the observer. At the very threshold of the event horizon, from the outsider's perspective, time for the falling object would appear to stop completely. It would seem to hover, frozen forever, a fossilized moment etched onto the edge of darkness. Of course, this frozen image is an illusion from a distant vantage point. For the object itself, crossing the horizon would be uneventful, a passage through a silent, one-way door. The Schwarzschild metric gives us the foundational framework to calculate these bizarre effects with precision. It allows us to predict exactly how much time will slow near any spherical mass, from a planet to a star to the most fearsome black hole. This elegant set of equations transforms the philosophical wonder of warped time into a measurable, predictable phenomenon. But what does this mathematical certainty feel like? What would it be like to actually approach this ultimate boundary, not as an equation, but as an experience? Yet this abstract concept is not confined to the far reaches of space. It is a measurable reality right here on our own planet. The difference is incredibly subtle, but it is there. If you were to place two perfectly synchronized atomic clocks in different locations, one at the top of a tall mountain and the other at sea level, they would slowly drift out of sync. The clock at the lower altitude, subjected to just a slightly stronger pull from Earth's gravity, would begin to tick slower than its elevated counterpart. Over the course of a year, the difference would amount to mere microseconds, but it is undetectable. This is not a theoretical exercise. It is a daily consideration for one of our most vital technologies. The Global Positioning System, or GPS, relies on a network of satellites, each carrying a hyper-accurate atomic clock. These satellites orbit high above Earth, in a region where our planet's gravity is measurably weaker. Because of this, the clocks on the satellites run faster than identical clocks on the ground. If the engineers who designed the system did not deliberately program the satellites to tick slightly slower before launch, the entire network would fail. The timing errors would accumulate so quickly that your phone's navigation would be off by several kilometers after just a single day. This is not a minor correction. It is a fundamental admission that Einstein was right. We live in a universe where the flow of time depends on your gravitational address. The precise engineering of our GPS is a quiet, continuous testament to a warped reality, a whisper of the same cosmic forces that near a black hole become an all-consuming roar. That staggering density is the key to their power over time. A single sugar cube of neutron star material would weigh billions of tons, a mass so incomprehensible that it warps the local fabric of spacetime into a deep, steep well. If you could place a clock on that incredibly solid surface, you would witness time dilation in action. Its ticks would be slower, more drawn out, compared to the steady beat of an identical clock floating in the emptiness of space. This is not a tiny, microsecond effect like we see on Earth. The difference here is significant, a direct and powerful consequence of the star's ferocious gravity. So how do we know this is truly happening? We cannot land a probe on a neutron star, but nature has provided us with perfect natural laboratories known as pulsars. These are neutron stars that spin at incredible speeds, beaming out radiation from their magnetic poles like cosmic lighthouses. As they rotate, these beams sweep across space, and if one points toward Earth, we detect a remarkably regular pulse of radio waves. The timing of these pulses is so precise that it rivals our best atomic clocks. Astronomers use this celestial metronome to probe the star's environment. They can detect minute changes in the pulse timing, variations that are perfectly explained by the passage of those radio waves climbing out of the neutron star's deep gravitational well. The waves lose energy in their escape, and their rhythm is subtly altered, providing brilliant, indirect proof that time itself is running slower at the source. By studying these exotic objects, we are conducting fundamental experiments in relativity under conditions we could never hope to recreate. The matter on a neutron star is crushed into states that defy our earthly understanding, a bizarre soup of subatomic particles governed by the unyielding rules of Einstein's geometry. Each precise pulse from a distant pulsar is a message, a data point sent from a realm where gravity has truly taken command of time. This ultimate boundary, the event horizon, marks a silent and final frontier. It is the precise point around a black hole where the pull of gravity becomes so overwhelming that the escape velocity equals the speed of light. Since nothing in the universe can exceed that ultimate speed limit, crossing this line is a one-way journey. Nothing that passes through can ever send back any information, any light, any signal at all. The event horizon acts as a perfect cosmic veil, separating the world we can know from the profound unknown that lies within. From our distant, safe vantage point, we would witness a truly bewildering spectacle if we were to watch an object fall toward this edge. As it approaches the horizon, the object would appear to slow down dramatically, as if moving through an invisible, thickening syrup. Its light would stretch and redden, shifting toward longer, lower-energy wavelengths in a process called gravitational redshift. The image would also grow progressively dimmer, fading like a dying ember. From our perspective, the object would never actually cross the line. It would appear to hover, its final moment stretched across eternity, forever frozen in time just outside the darkness. This is the distant observer's reality, a fossilized image painted by the extreme warping of spacetime itself. Yet, for the astronaut making that fateful plunge, the experience is entirely different. Their personal clock ticks forward at its normal, familiar rate. There is no sudden jolt, no alarming signpost as they pass through the event horizon. The crossing is silent and geometrically smooth. If the black hole is large enough, the difference in gravitational pull from their head to their feet, known as tidal forces, might be negligible at first. They would simply float through this one-way door, drawn inexorably toward the mysterious singularity at the center. This creates a profound paradox. Two realities exist simultaneously. For us, the outsider, the astronaut is frozen forever at the threshold. For the astronaut, that same threshold has come and gone in an instant. This is not a trick of perception, but a fundamental feature of relativity. There is no single, universal now. The flow of time is a deeply personal experience, shaped entirely by your position and motion within the cosmic fabric. The event horizon forces us to abandon the comforting idea that everyone shares the same present moment. It reveals a universe where now is a local phenomenon, and where the ultimate boundary in space is also the place where our common sense understanding of time completely unravels. But the warping of time and space is only the beginning. Around a spinning cosmic giant, spacetime itself begins to swirl. This phenomenon, known as frame dragging, is like submerging a spinning ball into a vat of thick honey. The honey closest to the ball does not just sink into a depression, it gets caught and twisted, forced to circulate around the spinning surface. In the same way, a rotating massive object like a planet, a neutron star, or especially a black hole, does not just create a static gravitational well. It pulls the very fabric of spacetime into a vortex, dragging it along in the direction of its rotation. This means that an object falling toward such a body is not only pulled inward by gravity, it is also swept sideways, caught in a cosmic whirlpool that it cannot resist. The mathematics that first described this for a rotating black hole is called the Hafele-Keating Solution, and it revealed a universe far more dynamic than even Einstein might have initially envisioned. In this solution, the event horizon is different, and there exists a region outside of it called the ergosphere, where resisting the spin of the black hole becomes impossible. Everything, including spacetime itself, is forced to move. This is not just a theoretical idea for distant black holes. The effect is present, albeit incredibly faintly, right here in our own celestial neighborhood. A satellite mission named Gravity Probe B was launched with a remarkable goal: to measure the frame dragging caused by the Earth's rotation. The satellite contained gyroscopes of unparalleled precision. In a universe governed by Newton's laws, the spin axes of these gyroscopes would have pointed in a fixed direction forever. But in Einstein's universe, the slow, gentle twisting of spacetime around our spinning planet should cause the gyroscopes to drift ever so slightly over time. After years of painstaking data collection, the results confirmed it. The Earth, simply by turning, drags the framework of reality around with it. This confirmation shows that gravity's influence is not a simple, static pull. A massive object can set the very stage of the universe into motion, forcing the coordinates of space and time to dance to its rotation. This cosmic drag on spacetime has a brilliant optical consequence. If a massive object can pull the fabric of reality, then it can also bend the very path of light itself. This is gravitational lensing, a phenomenon where the gravity of a cosmic giant acts like a vast, natural magnifying glass. Think of a wine glass on a printed page. The curved glass distorts the letters behind it, stretching and warping them into strange, elongated shapes. In the depths of space, an entire galaxy cluster can perform the same trick. Its immense collective gravity creates a profound curvature in spacetime. When light from a more distant galaxy travels through this warped region, its path is no longer straight. It bends, twisting around the foreground cluster on its long journey to our telescopes. The result is not just a blur. We see multiple smeared or duplicated images of the same background galaxy. In a perfect alignment, the light forms a complete circle around the foreground mass, a stunning structure known as an Einstein ring. These are not mere cosmic curiosities. They are direct, observable proof that spacetime is curved. Each distorted arc is a map of the gravitational field, a silhouette of the invisible warping created by mass. But what if the mass we can see does not fully account for the lensing effect we observe? This is where the phenomenon reveals something even deeper and more mysterious. The lensing is often far stronger than the visible matter alone can explain. The only way to account for this is through the presence of dark matter, an invisible substance that permeates the cosmos, exerting a gravitational pull but emitting no light. By studying how the light is bent, astronomers can essentially weigh the lensing cluster. They can calculate the total mass required to create the distortion they see, and in doing so, they create a map of where the dark matter must be. Gravitational lensing has thus become one of our most powerful tools. It confirms the geometric nature of gravity, allows us to peer at galaxies too faint to see otherwise, and unveils the hidden architecture of the universe, all by watching how the cosmos bends its own light. This strange separation of realities is perfectly captured in a classic thought experiment, the twin paradox. Imagine a pair of identical twins. One remains safely on Earth, while the other embarks on a journey through space at a speed approaching the speed of light. When the traveling twin finally returns home, a shocking difference is revealed. The astronaut twin is younger than the sibling who stayed behind. Their clocks are out of sync, and so are their lives. This is not science fiction. It is a direct prediction of special relativity, where motion itself can stretch time. But there is a parallel version of this story, one governed by gravity rather than speed. If one twin lived on the surface of a dense, high-gravity world like a neutron star, while the other floated in the weightlessness of high orbit, the outcome would be the same, only the cause would differ. The twin enduring the stronger gravity, feeling the deeper pull of that cosmic well, would age more slowly. Their biological clock would tick fewer times. They would return to their sibling, having experienced less of the universal flow of time. The puzzle of the paradox lies in a seeming contradiction. If all motion is relative, why is the traveling twin the one who ages less? Why is it not a matter of perspective? The resolution is found in a critical detail, an asymmetry in their journeys. The twin who travels does not simply move at a constant speed. To leave Earth, to turn around, and to land back home, they must accelerate. They feel the forces of their rocket engines pushing them back into their seats. The twin on Earth feels no such sustained acceleration. It is this physical difference, this breaking of the perfect symmetry, that makes the age difference real and absolute. It is not an illusion. It is a permanent physical change written into the very fabric of their being. The same applies to the gravitational version. The twin on the high-gravity world is constantly experiencing the acceleration of standing on its surface, pushing back against that immense pull. Their path through the warped spacetime is fundamentally different from their sibling in the weaker field of orbit. This thought experiment forces us to let go of a deeply ingrained belief, the idea of a single, universal clock ticking for everyone, everywhere. There is no master timekeeper for the cosmos. Your personal time, the rate at which you experience the universe, is your own. It is a local phenomenon dictated entirely by your own motion and the gravitational terrain you are passing through. The universe does not have a shared present moment. It has a tapestry of nows woven together by the paths we take through the curved geometry of reality. The silent dance of two black holes is a performance written in the geometry of spacetime itself. As these cosmic giants orbit one another, locked in a final embrace, they do not simply move through space. They churn it, their immense masses spinning at a fraction of the speed of light, whip the very fabric of reality around them, sending out ripples that travel at light speed across the cosmos. These are gravitational waves not made of matter but of pure spacetime curvature. For decades, they were only a prediction of Einstein's theory, a subtle consequence of his equations that many thought we would never actually detect. Then, in 2015, an experiment of almost unbelievable precision proved him right once more. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, heard the faint echo of a universe ringing like a bell. The signal came from an event more than 1 billion light-years away, where two black holes, each dozens of times more massive than our Sun, spiraled inward and merged into one. In the final fraction of a second before their collision, they released more power in gravitational waves than all the stars in the observable universe combined. This was not a flash of light or a burst of radiation. It was a literal vibration in the structure of reality, a tremor that stretched and squeezed the space on Earth by a distance far smaller than the width of a single proton. That we could measure this at all is one of the greatest technical achievements in human history. The event itself was a perfect laboratory for the most extreme physics. The velocities involved were a significant fraction of the speed of light, and the gravitational fields were so intense that time itself was wildly distorted in the vicinity of the merging pair. The specific pattern of the ripples we detected, the rising chirp that ended in a final, defining ring, carried encoded within it the story of the collision. By reading this cosmic message, scientists could deduce the masses of the original black holes and the mass of the final, single object they became, confirming that a portion of their combined mass had been converted into pure energy of the waves, exactly as Einstein's equations predicted. This new sense of hearing the cosmos has transformed our understanding. We are no longer limited to observing the universe through light alone. We can now listen to the faint whispers of spacetime, the echoes of collisions that happened in the dark, silent voids between galaxies. Each gravitational wave signal is a direct probe of gravity operating in its most ferocious regime, a stringent test that, so far, general relativity has passed with flying colors. We are witnessing the dynamic, living nature of the cosmos, a place where space itself can be compressed and stretched, and where the most violent events are written in a language of pure geometry. This deep freeze of information at the event horizon creates one of the most perplexing puzzles in modern physics. We are faced with two sets of rules, both incredibly successful in their own domains, that appear to give completely different answers. General relativity, which describes the large-scale structure of the cosmos, tells us that an object falling into a black hole simply crosses the horizon and is lost, with all the information about its makeup seemingly erased from our universe. Yet quantum mechanics, the rules governing the very small, states with absolute certainty that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. This direct conflict is the heart of the black hole information paradox. It is as if the universe has two contradictory legal systems, and a black hole is a crime scene where both sets of laws have been broken. The information about the fallen object, the specific arrangement of its atoms, its history, its identity, appears to vanish. From our distant perspective, it is smeared and frozen onto the surface of the horizon, a ghostly hologram that never quite falls in. But for the object itself, it passes through into the unknown interior. So where does the information truly go? Does it remain stored on the horizon like data on a cosmic hard drive? Or is it truly lost inside, violating a foundational principle of reality? This is not just a philosophical debate. Resolving this paradox is considered a crucial step toward a unified theory of quantum gravity, a framework that would seamlessly blend the laws of the very large with the laws of the very small. Such a theory would describe the fabric of spacetime not as a smooth continuum, but as something built from discrete, tiny building blocks at the Planck scale. Perhaps at this unimaginably small level, the event horizon is not a sharp boundary but a turbulent quantum froth where information is preserved in some new, exotic way. The fate of a single bit of information falling into a black hole may hold the key to understanding the true, fundamental nature of reality itself. Yet this cosmic fabric is not woven from the stars and galaxies we see. The brilliant clusters and swirling nebulae are merely the visible embroidery on a far darker tapestry. The overwhelming majority of the universe's content, nearly 95% of it, is made of substances we cannot see, dark matter and dark energy. Their nature remains one of physics' greatest mysteries, and while they do not create the intense, local time warps of a black hole, they command the grand architecture of spacetime itself. Dark matter acts as the universe's hidden skeleton. We cannot see it because it does not emit, absorb, or reflect light, yet we know it is there because of its powerful gravitational grip. Its invisible pull is what holds fast-spinning galaxies together, preventing them from flying apart. It is the gravitational glue for immense galaxy clusters, and as we have seen, it is this gravity that we map through the bending of light in gravitational lensing. Dark matter's mass dictates the largest curves in the cosmic fabric, shaping the vast gravitational wells that entire galaxies slide through. Then there is dark energy, an even more enigmatic presence. It is not a pulling force, but a pushing one, a property of empty space itself that drives the expansion of the universe to accelerate. Think of the fabric of spacetime not as a static sheet, but as rising bread dough, with dark energy causing the dough to expand faster and faster, stretching the very distances between galaxies. This relentless expansion has a direct, relativistic effect on our perception of time across the cosmos. The light from the most distant galaxies is stretched to longer, redder wavelengths as it travels through this expanding space, a phenomenon known as cosmological redshift. But this stretching is more than just a color shift. It is a stretching of time itself. The very frequency of the light waves, the ticking of that distant cosmic clock, is slowed down by the expansion. We are seeing those ancient galaxies in extreme slow motion, their light a relic from an era when the universe was younger and its expansion rhythm was different. To grasp the full picture of cosmic reality, from the frozen moment at a black hole's edge to the deep time of the universe's history, we must acknowledge these dark architects. They write the rules for the largest stage, governing how spacetime curves and evolves on a scale that dwarfs even the most massive singular objects. Their silent influence reminds us that the true nature of gravity and time is a story still being written, with most of its main characters still hidden in the shadows. Even Einstein's equations hold secrets more fantastic than black holes. Deep within the mathematics of general relativity, there exists the tantalizing possibility of wormholes. These are not tunnels through space, but shortcuts through the very fabric of spacetime itself. Picture a vast folded piece of paper with two distant points lying far apart. A wormhole would be like a pencil hole punched straight through the fold, connecting those points in an instant. Such a structure, often called an Einstein-Rosen bridge, would theoretically allow a journey across thousands of light years in a single step. But this cosmic shortcut comes with a universe of problems. The equations show that these tunnels would be incredibly unstable. The moment even a single photon tried to pass through, the wormhole would snap shut like a rubber band, crushing anything inside. To hold this gateway open, to make it traversable, would require a substance that defies our current understanding of physics, exotic matter. This is not just unusual material, but something with a negative energy density, a form of matter that would effectively push spacetime apart rather than pulling it together. We do not know if such a substance can truly exist. If a stable wormhole could be forged, the effects on time would be as dramatic as the effects on space. The intense gravity at each mouth of the tunnel would warp time in different ways. Imagine one end of the wormhole placed near a powerful gravitational field, like a neutron star where time passes slowly. The other end rests in the empty void of interstellar space where time flows faster. This creates a natural time machine, an astronaut stepping into the slow time mouth and emerging from the fast time mouth would not just travel across space, they would travel into the future of the outside universe. Even more bizarrely, by moving the mouths of the wormhole relative to each other, the theories suggest one could create a path into the past. This is where the physics collides with profound paradoxes. What if you traveled back in time and prevented your own journey? This famous grandfather paradox highlights the logical impossibilities that such backward time travel introduces, challenging our most basic notions of cause and effect. While no evidence for wormholes exists, and they may forever remain in the realm of theoretical mathematics, their study pushes our understanding to the absolute limit. They force us to ask how far the fabric of reality can be stretched, twisted, and connected, revealing a cosmos where the lines between science fiction and fundamental physics are beautifully, and perhaps permanently, blurred. The precise strength of gravity feels like a given, a simple fact of our universe. Yet this seemingly fixed number holds profound consequences for the flow of time and the potential for life itself. Our ability to think, to grow, and to experience a stable reality depends on a cosmic balancing act of incredible delicacy. This idea is known as the Anthropic Principle. It suggests that the fundamental constants of nature, like the force of gravity, appear finely tuned to allow for the existence of observers who can measure them. It is not that the universe was designed for life, but rather that we find ourselves in one of the vanishingly rare cosmic environments where life became possible at all. Consider a world where gravity was just a few times stronger than it is. The time dilation on a planet's surface would be severe, not the subtle microsecond effects we measure on Earth. A single heartbeat could stretch into an hour from the perspective of a distant star. The intricate, rapid-fire chemical processes that form the basis of biology, the dance of neurons in a brain, would be thrown into chaos. Life as we understand it, dependent on a consistent and reliable flow of time, simply could not arise. We are here because we live in a gravitational sweet spot. Our planet orbits within a habitable zone of space, but we also exist within a habitable zone of physical law, where the strength of gravity and the resulting nature of time are just right for complex structures to form and persist. This connection ties the grandest cosmic forces directly to our own existence. The fact that we are here to wonder about black holes and warped time is itself a data point. It tells us that our universe is one where the rules of physics allow for the emergence of curious minds to gaze back at the cosmos and decipher its deepest, most beautiful mysteries. But the smooth, geometric fabric of spacetime described by Einstein begins to fray at the very smallest of scales. To grasp the true nature of gravity, we must reconcile two seemingly incompatible visions of reality. On one hand, we have general relativity, which paints the cosmos in broad, elegant strokes, describing how planets, stars, and galaxies curve the stage of the universe. On the other, we have quantum mechanics, the bizarre and counterintuitive rules that govern the frantic dance of atoms and subatomic particles. Each theory is spectacularly successful in its own domain, yet they speak different languages and obey different laws. Unifying them into a single, coherent theory of quantum gravity stands as the paramount challenge in modern physics. It is a quest to answer a deceptively simple question: what is spacetime made of, right down at its very foundation. The search has led to ambitious frameworks like string theory, which proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy. Their different vibrations could give rise to all the forces and particles we see, with gravity emerging naturally from the mix. Another compelling approach is loop quantum gravity, which suggests that space itself is not a continuous canvas, but is woven from a network of finite, discrete loops. Picture the smooth surface of a pond. From a distance, it appears perfectly continuous, but if you could look closely enough, you would see it is made of countless, individual water molecules. In this view, spacetime has a fundamental graininess, a pixelated structure at the tiniest possible scale, known as the Planck length. At this level, the serene geometry of Einstein's universe might be replaced by a chaotic, frothing quantum foam, where tiny wormholes blink in and out of existence and concepts like before and after lose all meaning. This has a staggering implication for our understanding of time. If spacetime itself is quantized, then time may not be a fundamental river flowing through the universe. Instead, our experience of time, the relentless forward march from one moment to the next, could be an emergent property. It might arise from the changing relationships between these countless quantum building blocks, much like the illusion of smooth motion arises from the rapid succession of still frames in a film. The profound slowing of time near a black hole would then be a large-scale manifestation of a deep, microscopic truth. Solving this puzzle would not just complete our picture of the cosmos, it would fundamentally redefine our place within it, revealing that the very stage upon which reality plays out is itself a magnificent and dynamic construction. Our own conscious experience presents a powerful contradiction to the frozen cosmos of relativity. We feel time as a relentless current, carrying us from a fixed past into an uncertain future. Yet the physics of spacetime insists this flow is not a fundamental feature of the universe. This is the core of the block universe theory, a view where time is just another dimension, much like length or width. In this four-dimensional reality, the past, present, and future do not happen one after another. They simply are, eternally coexisting. Your birth, your life, and every moment of your future are all equally real, fixed points in the vast, static sculpture of spacetime. The feeling of a moving now, this vivid present moment we all share, has no special status in the equations. It might be a profound illusion generated by our own consciousness, a trick of the mind as it processes a world of immense complexity. Another key to this illusion may be thermodynamics, specifically the concept of entropy, which is a measure of disorder. The universe as a whole moves from states of lower entropy to higher entropy, from order to disorder. We remember the past because it was more ordered, and we perceive time's arrow because we are part of this grand, one-way process. A broken cup shatters and does not reassemble itself. Memories form but are not unmade. This relentless increase in entropy gives our lives a narrative direction, creating the undeniable sensation that time is flowing forward. The extreme time dilation near a black hole makes this philosophical puzzle tangible. If you were to observe a friend falling toward an event horizon, you would see their time slow to a complete halt from your perspective. Their entire future from that point onward is laid out before you, frozen at the threshold. This is not just a distortion of clock ticks. It is a direct visual demonstration that one person's future can literally become another person's past, all depending on their position in the gravitational landscape. There is no single, universal present. Your now and the now of someone near a cosmic giant are not the same. The block universe does not invalidate our experience of life, our joys, or our choices. Instead, it expands our understanding of reality to a cosmic scale, suggesting that the river of time is a local current within a much deeper, more mysterious, and perhaps timeless ocean. A world where a few hours for one person can mean a lifetime for another is no longer just a fantasy. The film Interstellar gave us a breathtaking visual of this very principle, with astronauts on a planet near a massive black hole experiencing mere hours while decades unfolded back on Earth. This powerful depiction was not pure artistic invention. The filmmakers worked closely with Nobel laureate physicist Kip Thorne, using the actual equations of general relativity to generate the stunning visual effects of the black hole gargantua. The result was a scientifically plausible, though dramatized, vision that made an abstract concept viscerally real for millions. This collaboration between science and cinema serves a profound purpose. It translates the cold mathematics of relativity into a human story we can feel, sparking wonder and curiosity about the true nature of our universe. Yet, it is always crucial to recognize where artistic license takes over. The rapid passage of time on the water planet, for instance, was amplified for narrative impact, compressing an effect that would typically require even more extreme conditions. This is the beautiful tension and responsibility of science fiction. It stretches our imagination, pushing the boundaries of what we believe is possible, and in doing so, often inspires the next generation of scientists to ask the very questions that turn fiction into fact. The cinematic journey to the stars is a gateway, inviting us all to look up and question the fundamental rules of reality. The theory was no longer just elegant mathematics on a page. It was a prediction waiting for a test, and in 1971, physicists Hafele and Keating designed a brilliant one. They took state-of-the-art atomic clocks, placed them aboard commercial airliners, and flew them around the world. Another set of identical clocks remained securely on the ground. The plan was simple yet profound. After the journeys, the clocks were compared. The results were undeniable. The clocks that had flown at high altitude and high speed were out of sync with the stationary ones, and the difference perfectly matched the predictions of relativity. The experiment had to account for two separate effects. The speed of the airplanes relative to the Earth rotation caused a slight slowing of time due to velocity, a key part of special relativity. Simultaneously, the weaker gravity at the high flight altitude caused a slight speeding up of time, a result of general relativity. The final time difference was a tiny fraction of a second, but it was there, a tangible fingerprint of a warped reality. This was not a thought experiment anymore. It was a direct measurement proving that time itself is a traveler, its pace dictated by both motion and gravity. Today, our tools have grown exponentially more sensitive. Modern optical atomic clocks are so astonishingly precise that they can detect the passage of time slowing down if you lift one just a few centimeters higher than its twin. On this minute scale, the clock on the floor truly does tick slower than the clock on the table. This is not a laboratory curiosity. It is the relentless refinement of our understanding, turning a cosmic principle into a daily engineering reality. Every time a satellite beams a signal to your phone, it carries with it the quiet, continuous confirmation of those flying clocks from decades ago. The universe is not built on a rigid, universal clock. It is a fluid tapestry of individual moments, and we now have the instruments to watch it breathe. This faint, cosmic static is the oldest light in the universe. The cosmic microwave background radiation is an afterglow, a fossilized echo from a time when the cosmos was a mere 380,000 years old. Before this moment, the universe was a searing, opaque fog of plasma, too dense for light to travel freely. As it expanded and cooled, the first atoms formed, and the universe suddenly became transparent. That first flash of light, released in every direction, has been traveling for over 13 billion years. But the expansion of space itself has done something remarkable to this ancient radiation. It has stretched the very fabric of the light waves, pulling them from the energetic, visible part of the spectrum all the way down to long, low-energy microwaves. This is cosmological redshift in its most profound form, a direct and continuous time dilation effect. The wavelength of each photon has been stretched by the expanding universe over its immense journey, a literal slowing of its vibrational rhythm across the eons. By studying the precise patterns in this microwave hum, cosmologists can read the story of the cosmos like a cosmic fingerprint. The tiny temperature fluctuations in this background reveal the seeds of all future structure, the slight overdensities that would one day collapse into the vast cosmic web of galaxies and clusters. This relic radiation allows us to measure the geometry of the universe on its largest scales, confirming it is flat, and to calculate its precise composition of ordinary matter, and dark energy. It is our most direct link to the infancy of everything, a snapshot of spacetime itself when it was young and simple, offering a silent testimony to the moment the curtain lifted on the cosmic stage. Gravity feels like a constant, familiar presence, yet it hides a deep cosmic mystery. Its pull is astonishingly feeble compared to the other fundamental forces. The electromagnetic force that holds atoms together is stronger than gravity by a factor of 1 followed by 40 zeros. This staggering mismatch is known as the hierarchy problem, and it begs a simple question: why is the force that shapes galaxies and planets so incredibly weak on the subatomic scale? One compelling, though speculative, answer suggests that gravity is not weak at all. It only appears that way from our limited, three-dimensional perspective. Some theories, including certain versions of string theory, propose that our universe may contain more than the 3 spatial dimensions we experience. These extra dimensions would be curled up or compactified at a scale trillions of times smaller than an atom, completely invisible to us and to every particle and force except one, gravity. In this view, the gravitational field generated by any object does not just spread out across our 3 dimensions. It also leaks or dilutes into these hidden, microscopic dimensions. This leakage would explain why gravity seems so faint to us. We are only feeling a tiny fraction of its true strength, with the rest escaping into a realm we cannot perceive. This radical idea has profound implications for the nature of reality. If these extra dimensions exist and could somehow be probed, the behavior of gravity and even the warping of time near massive objects might be dramatically different from what Einstein's equations predict in a purely 4-dimensional universe. The way a black hole bends spacetime or how a neutron star slows time could be subtly altered by the hidden architecture of the cosmos. While there is no experimental evidence for this yet, these theories push the boundaries of our imagination. They suggest that our current understanding of gravity and time is not the final word, but merely a shadow cast by a far richer, more complex reality existing in dimensions beyond our own. This loss of energy reveals itself as a color shift, a cosmic fatigue painted in light. As a photon struggles against the immense gravity of a star or a black hole, it does not slow down since light always travels at the same speed. Instead, it loses energy in a different way by stretching out. Its wavelength grows longer, shifting its color from the blue end of the spectrum toward the red. This is gravitational redshift, a direct and elegant confirmation that gravity steals energy from light itself. The effect is incredibly subtle here on Earth, but in 1959, physicists Robert Pound and Glenn Ribcam managed to measure it. They sent a beam of gamma rays down a tower at Harvard University and measured the tiny but precise redshift as the light fell downward, gaining energy, and then again as it traveled upward, losing energy to Earth's own gravity. Their experiment was a masterpiece of precision, confirming a key prediction of general relativity just a few decades after it was proposed. But near a cosmic giant, this subtle shift becomes an overwhelming transformation. Consider light emanating from the surface of a neutron star or from just outside a black hole's event horizon. It begins its journey as visible light, perhaps even as energetic X-rays. But as it climbs out of that bottomless gravitational well, it loses so much energy that its wavelength is stretched far beyond the red, into the realm of infrared, then microwaves, and eventually into long, weak radio waves. From our distant perspective, the light from near the event horizon is redshifted into total invisibility. It fades to black, not because it has been blocked, but because its very essence has been drained by gravity. This phenomenon is not separate from the slowing of time. It is the very same effect observed through a different lens. The frequency of a light wave is a clock, a regular, ticking oscillation. If time itself is running slower in a powerful gravitational field, then those ticks are farther apart and the wave is stretched. Gravitational redshift is time dilation made visible, a silent, colorful testimony to the fact that where gravity rules, even light must pay a toll. This radical simplicity is known as the No-Hair Theorem. It tells us that a black hole, for all its terrifying power, is a fundamentally simple object. An isolated black hole can be completely described by just three numbers: its mass, its electric charge, and its spin. Think of the most complex object you can imagine: a star teeming with nuclear fusion, a planet rich with oceans and mountains, or even a living being with its intricate history. If any of these were to fall into a black hole, every last bit of that stunning complexity would be seemingly erased. The specific arrangement of atoms, the chemical signatures, the very identity of what fell in, all of it is lost. From the outside, the black hole would simply grow slightly more massive. Its spin might change a fraction, and that would be it. The only thing left would be a perfectly smooth, featureless event horizon, a silent sphere hiding an immense secret. This idea has staggering implications for the nature of reality. It suggests that information, the detailed data that makes a thing what it is, can be truly and permanently destroyed. This directly challenges a core principle of quantum mechanics, which states that information is never lost, only scrambled. The No-Hair Theorem places these two pillars of modern physics on a direct collision course, creating the famous information paradox. How can a universe that seems to conserve information at the most fundamental level also contain objects that act as ultimate shredders? The resolution to this puzzle may lie in the mysterious singularity at the black hole's heart, a point where the known laws of physics break down entirely. The No-Hair Theorem forces us to confront a humbling thought. The most massive and fearsome objects in the cosmos are, in their final expression, almost elegantly simple, their internal chaos veiled by a horizon where our understanding of space and time reaches its limit. Even the emptiest void in the universe is not truly empty. In the profound silence between stars, at a scale far smaller than an atom, a frantic dance of creation and destruction is constantly unfolding. This is the realm of quantum fluctuations, where so-called virtual particles spontaneously pop into existence, borrowing energy from the vacuum for a fleeting moment before annihilating each other and vanishing back into nothingness. This ceaseless activity is normally invisible, its effects cancelling out perfectly. But in 1948, a physicist named Hendrik Casimir predicted a way to make this hidden energy tangible. He envisioned placing two perfectly smooth, uncharged metal plates extremely close together in a vacuum, so close that the gap between them is smaller than the wavelength of most virtual particles. This creates a restriction. Only certain wavelengths of quantum fluctuations can fit between the plates, while a wider variety can exist outside them. The result is a subtle imbalance in this sea of quantum energy. The greater pressure from the fluctuations outside pushes the plates together with a faint but measurable force. This is the Casimir effect, and its experimental confirmation was a revelation. It proved that what we call empty space is actually a seething, energetic medium. This quantum activity is not just a curiosity for particle physics. When we extrapolate this idea to the very foundation of reality, to the unimaginably small Planck scale, some theories suggest that these fluctuations are not just happening in spacetime, they are happening to spacetime. The very fabric of the cosmos might be a turbulent quantum foam, a bubbling sea where tiny wormholes and baby universes blink in and out of existence. In this view, perfectly flat, smooth spacetime is a large-scale average, an illusion created by this underlying chaos. If this is true, then the flow of time itself, which seems so steady and reliable, might also be subject to this microscopic churning. The relentless tick of a clock could be the net result of countless random fluctuations in the geometry of reality, a profound hint that our experience of time is rooted in the deepest, most dynamic structure of the universe. This ultimate breakdown, the singularity, is the final destination of the black hole's immense gravity. All the mass that has ever crossed the event horizon is thought to be crushed into an infinitely dense, infinitely small point. Here, the curvature of spacetime becomes infinite, and the very laws of physics, the rules that have guided our understanding from the smallest particle to the largest galaxy, simply cease to function. The equations of general relativity, which so beautifully describe the warping of the cosmos, output a result that means nothing, a division by zero in the fabric of reality. The existence of this point is not a victory for physics, but a glaring signpost indicating its limits. It tells us with absolute certainty that our current theory is incomplete. It cannot handle the extremes it itself predicts. To peer into this void and understand what truly happens, we require a new set of rules, a theory that can marry the vast cosmic landscape of relativity with the frantic, probabilistic world of the quantum. This sought-after theory of quantum gravity would describe reality at this unimaginable scale, perhaps revealing that the singularity is not a point of infinite density, but something else entirely. Perhaps spacetime is not a smooth continuum that can be stretched indefinitely, but is woven from discrete, tiny grains. In such a picture, there would be a smallest possible unit of space and a smallest possible unit of time, preventing the formation of true infinities. The crushing grip of a black hole would then compress matter to this fundamental limit, but no further. The singularity would be replaced by a region of extreme, yet finite, density where the quantum nature of gravity takes command. Resolving this problem is not just about cleaning up a mathematical inconvenience. It strikes at the heart of what we consider real. If our concepts of space and time break down at the universe's most powerful objects, then we must be prepared for a new picture of reality's foundation. One where the familiar dimensions of our world emerge from a deeper, more fundamental layer of existence. These same equations that predict black holes also contain a mirror image, a cosmic opposite known as a white hole. If a black hole is a one-way street where matter and energy can only fall in, a white hole would be its time-reversed twin, a region of space-time from which matter and energy can only erupt outward. Nothing from the outside universe could ever cross its boundary into this cosmic fountain. While we have overwhelming evidence for black holes, no astronomical object has ever been identified as a white hole. Most physicists consider them to be mathematically elegant but physically unlikely, a beautiful ghost in the machinery of relativity. Yet their existence within the math forces a profound question. The fundamental laws of physics, from gravity to quantum mechanics, are almost entirely reversible. They work just as well whether time runs forward or backward. So why does our universe exhibit such a strong, one-way arrow of time? Why do we remember the past but not the future? Why does an egg, once scrambled, never unscramble itself in its bowl? The presence of white holes in Einstein's cosmos suggests that a universe with a reversed flow of time is not logically impossible. It hints that the relentless forward march we experience may not be a fundamental rule written into the fabric of spacetime, but rather a large-scale feature of our particular cosmic environment. Perhaps it is a consequence of the unique, low-entropy state of the Big Bang, a single initial condition that set the entire universe on a one-way path of increasing disorder and complexity. To consider a white hole is to glimpse a cosmos where cause and effect could, in principle, run in reverse, challenging our most basic assumptions about reality itself. Our universe might be a single page in an infinite cosmic library. This is the concept of the multiverse, a speculative but compelling idea suggesting that our reality, with its specific rules for gravity and time, is just one of countless others. In this vast cosmic ensemble, the fundamental constants could be shuffled into entirely different combinations. Imagine a universe where gravity is so strong that stars form and burn out in a single earthly day. In another, gravity might be so weak that galaxies never coalesce from the primordial gas. The very nature of time could be alien, perhaps flowing in multiple directions at once or not existing as a dimension at all. In such a landscape, our own reality appears incredibly fine-tuned, a rare bubble where the conditions were just right for the slow, steady dance of galaxies, stars, and life to unfold. This idea stretches the implications of warped time to their ultimate conclusion. If gravity's strength is a local variable, then the profound time dilation near a black hole is not an absolute truth of reality, but merely a feature of our particular cosmic neighborhood. The rules we are uncovering might be the local bylaws of our universe, not the fundamental constitution of existence. This naturally leads to another mind-bending question, the possibility of alternate timelines. The same mathematics that allows for wormholes and intense time dilation also permits hypothetical pathways called closed time-like curves, loops in spacetime that could, in theory, allow for travel into one's own past. Such a journey would instantly create a branching point, an alternate timeline where history unfolds differently. This is where we confront the classic grandfather paradox, where altering the past creates a logical inconsistency that seems to break causality. While these ideas remain firmly in the realm of theoretical exploration, they serve a vital purpose. They push our understanding of reality to its absolute limits, forcing us to question whether the flow of time and the strength of gravity are necessary features of the cosmos, or simply the unique signature of our own cosmic home. This debate between two fundamental views of time is far from abstract. It strikes at the very heart of our reality. On one side is presentism, the intuitive belief that only the present moment is truly real. The past is gone, a memory, and the future is not yet written. This is how we experience life, a single, moving point of now. Opposing this is eternalism, the view that past, present, and future all exist with equal reality. In this block universe, your birth, your life, and every moment of your future are fixed points in a vast, four-dimensional sculpture. Relativity does not merely suggest eternalism is correct, it demands it. Because time is relative, there is no universal clock, no single now that all observers across the cosmos can point to and agree upon. What is the present moment for you on Earth is already the deep past for an observer near a black hole, and the distant future for someone flying at near light speed. The severe time dilation near a cosmic giant makes this undeniable. Two events, like the beginning and end of a star's life, might appear to happen simultaneously for a distant astronomer. But for an observer hovering near that star, those same events could be separated by eons. Which perspective is the true present? The answer is that there is no privileged answer. This shatters the philosophical foundation of presentism. If there is no single objective present, then how can it be the only thing that is real? Our powerful, personal feeling of a flowing now, of time slipping from future to past, becomes a local phenomenon, a story our brains tell us as we navigate our particular slice of the cosmic block. Reconciling this subjective river of time with the objective, static landscape of space-time is one of the greatest challenges, not just for physics, but for understanding our own consciousness. It asks us to consider that our deepest experience of being may be a beautiful, necessary illusion, a flame of awareness flickering within an eternal, frozen structure. The ticking of an atomic clock is a whisper from the heart of reality itself. These modern marvels, the most precise timekeeping devices ever built, are now so sensitive they can detect the passage of time changing over the height of a single stair step. This is not just a laboratory curiosity, it is the key to a new way of seeing our own planet. By placing these ultra-precise clocks in different locations, from deep valleys to high mountains, and comparing their rates, we can measure the subtle variations in Earth's gravitational pull with stunning resolution. This emerging field, known as relativistic geodesy, transforms these clocks into gravitational cartographers. They are no longer just telling time. They are mapping the invisible landscape of gravity that shapes our world, revealing hidden aquifers, shifting tectonic masses, and the slow, silent flow of ocean currents, all by listening to the rhythm of time itself. This profound sensitivity also forces us to confront a fundamental challenge for our future among the stars. Consider a crew embarking on a multi-generational voyage to a distant star system, traveling at a significant fraction of light speed. For mission control on Earth, the journey might take centuries, but for the astronauts on board, their clocks would tick slower, a consequence of both their immense velocity and the weaker gravity of deep space. They might return to an Earth thousands of years in their future, having aged only decades themselves. This is not a paradox, it is a predictable outcome of relativity that must be factored into every aspect of mission planning, from life support and communication schedules to the very psychology of a crew unmoored from their original timeline. The cosmic principle that bends light around a galaxy also dictates the flight plan for a starship, transforming a theoretical wonder into the most practical of engineering concerns for any civilization that dares to reach beyond its cradle. Our search for alien life hinges on a simple, elegant idea: the habitable zone. This is the orbital region around a star where temperatures are just right for liquid water to exist on a planet's surface, a condition we believe is essential for biology as we know it. For stars like our Sun, this zone is a comfortable, life-giving band of space. But this familiar concept begins to warp and twist when we apply it to the most extreme environments in the cosmos. Imagine a world orbiting a neutron star or drifting in the gravitational shadow of a black hole. The sheer intensity of gravity in these regions would subject the planet to a profound and relentless slowing of time. The planet might still receive enough stellar radiation to theoretically possess liquid water, but the very rhythm of existence there would be fundamentally alien. A single orbit, which from our distant perspective might take one Earth year, could feel like the passing of a single day for a creature living on that world's surface. This is where our definition of habitability must expand beyond mere light and heat. We must now consider the local flow of time itself, the intricate dance of biological evolution, the slow drift of tectonic plates, even the chemical reactions that form the basis of life. All of these processes are governed by time. On a world where time is severely dilated, evolution could be accelerated or slowed to a crawl from our external viewpoint. An entire civilization might rise and fall in what we perceive as a single cosmic moment. This forces us to ask a deeper question: could life adapt to a reality where its internal clock is out of sync with the wider universe? The search for life is no longer just about finding the right place. It is about finding a place where the fundamental tempo of reality is compatible with the slow, steady, and beautiful process of becoming. Perhaps the most radical solution to the information paradox lies not within the black hole but on its surface. The holographic principle proposes a stunning idea that all the information describing everything within a three-dimensional volume is not contained inside it at all. Instead, it is perfectly encoded on its two-dimensional boundary like a cosmic hologram. Think of the security chip on your credit card. The flat, two-dimensional surface holds all the complex data needed to represent a three-dimensional object. In this view, our rich, three-dimensional reality, including the flow of time itself, might be a grand projection from a vast, two-dimensional surface at the edge of the universe. This principle was inspired by the study of black hole thermodynamics, where scientists found that the maximum information a black hole can hold is not proportional to its volume, but to the area of its event horizon. The horizon is not a passive membrane, but a dynamic surface where the information of everything that falls in is stored pixel by pixel. If this is true, then the intense time dilation near a cosmic giant is not a fundamental property of a deep, three-dimensional well. It is a feature of how information about time is encoded, processed, and projected from the boundary of that gravitational system. A single second stretched to an eternity near a black hole would be a consequence of the immense data density on its event horizon, a computational limit in the cosmic code. This idea transforms our crisis of lost information into a potential revelation. The information is not lost inside the black hole. It is smeared and preserved on its surface, a solution that could finally reconcile general relativity with quantum mechanics. The holographic principle asks us to consider that our entire universe, with its galaxies, stars, and our own conscious lives, might be a magnificent, immersive projection, a shadow play cast from the edges of reality. From the subtle drift of atomic clocks on Earth to the frozen moment at a black hole's edge, we have traveled a landscape where time itself is fluid. This bending near cosmic giants is far more than a theoretical oddity. It is a fundamental whisper about the nature of reality itself. Our journey reveals a universe where space and time are not a static stage, but a dynamic, interwoven fabric, perpetually shaped by the matter and energy within it. These are not just abstract rules governing distant stars, they are the hidden architecture of our existence, challenging our most basic perceptions of a steady, universal clock. Each discovery at the frontier, from gravitational waves to the information paradox, pushes the boundaries of science, pointing toward a deeper, quantum layer of reality waiting to be uncovered. Let this exploration be a starting point for your own curiosity. The cosmos is filled with mysteries that bend our understanding, so we would love to hear your thoughts on these wonders in the comments below. If you are ready for more journeys to the very edge of understanding, be sure to subscribe.